Hey, you're a college student in 1985, and whether it was intentional or not, you're taking the Putnam exam, the hardest the math test for math undergraduates. And the first problem you see is this one. Determine with proof the number of ordered triples A1, A2, A3 of sets which have the property that the union of A1, A2, A3 is equal to 1 through 10, and the intersection of A1, A2, A3 is equal to the null set. So let's see if you can give this a shot. Pause the video now and see if you can solve this problem, and we'll get back to the solution in a bit. Alright, did you solve it? Well, if not, don't worry. This is one of the hardest problems, so it's going to be a challenge for most people. But if you look at this problem, if you think about what does the union of A1, A2, A3 mean, that means that given these sets, you want the union to incorporate every single number from 1 through 10. This means that you could have 1, 2, 3, 4, 5, 6, or 7, 8, 9, 10 for A1, A2, A3. We call them A, B, and C here for more convenience. So another condition we have is A1 intersected with A2 intersected with A3. It's got to be the null set. That means there must be no overlaps between all three sets. You can have something like 1, 2, 3, and then B would have maybe something like 2, 3, 1, and then C has the remaining numbers. But you cannot have 1 in every single set. So how do you solve a problem like this? And I also forgot to mention, you can have A be the null set, B be the numbers 1 through 10, and C also be the null set. Well, the trick to solving this problem is actually to use binary. So what you do is you list out all the numbers from 1 through 10, and then say, under what conditions will this statement still hold true? In this case, for 1, you want 1 to have something like 1, you want A to have, we'll put 1 here to show that it's included in A, and 0 to show that it's not included in the set. So let's say 1 is included in A, it's not included in B, and it's not included in C. This looks good because when we do the union, we have 1 included in the whole set, and when we do the intersection, we know that B doesn't have it or C doesn't have it, so the intersection is not going to include it. So what about, let's do the next one. We can do something like maybe like 1, 1, 0. That means A has this number 2, B has the number 2, but C does not have the number 2. And when you intersect them, that means you still won't have the number 2 because all three of them do not have 2. And when you do the union, you'll definitely have 2 because A and B have 2. What if I did something like 1, 1, and 1? Well, this can't be true because in this case, even though the union will still have 3, the intersection will also have 3, so that doesn't satisfy our condition. So that's wrong. And what about 0, 0, 0? Well, the intersection certainly won't have 4, but the union will also not have 4, so that doesn't satisfy it either. In the end, we only have 6 combinations of E for each number that can be incorporated into this set. 1, 1, 0, which means 2 sets have it, A and B has it, C doesn't have it. 1, 0, 1, which means A has it, C has it, B doesn't have it, and so on. Like 1, 0, 0 is the first case where A has it, B doesn't have it, C doesn't have it, and kind of going on from there. So all in all, we've got 10 numbers and then 6 different ways of organizing those 10 numbers. So the answer is going to be 6 to the 10th power, or 2 to the 10th times 3 to the 10th. Not bad. Well, this was 1985. The problems have gotten a little bit harder since then, but hope you enjoyed this one. Thanks.